In this lecture, we are looking at the requirement for a titration. So first of all, we have an overview of glassware. You have used measuring cylinder, beaker, conical flask, volumetric flask, pipette, and burette. We can see that we have two groups here. The first group, we call them general glassware. They are for general use. The second group, we call them volumetric glassware. They are for precise, accurate measurements. You see that on each glassware, there's a circle on the neck of the tubes here. So the correct position to use this glassware is to raise them to your eyes level so you can see only a single line across the neck of the flask, the thin tube of the pipette, and of the burette. The volumetric flask is used to contain a certain amount of solution. We use volumetric flask to make standard solutions. The burette is to deliver accurate but variable volumes. We use it for the titrant. The pipette is also to deliver the solution, but it has fixed volume. We call it aliquot. We use a titration to determine the concentration of an unknown. We look at here an example of a titration to determine the concentration of hydrochloric acid from a titration with 0.1 mole per liter NaOH. So in this case, NaOH is the standard. So first of all, we pipette a certain volume of hydrochloric acid into a conical flask. We add some indicator in the flask. In our case now, we use phenolphthalein. A few drops of phenolphthalein is added into the conical flask. We see that the color of the solution here is colorless. Then we fill the burette with standard solution. We take the initial reading of the burette. We start the titration until the color of the solution in the conical flask turns pink. And we stop the titration. We take the final reading. The difference between the final reading and the initial reading is the volume of NaOH added to the conical flask. And we know that the neutralization reaction is HCl react with NaOH to give us NaCl and water. Terminology as we have covered. This is revision that solution in the burette is called titrant. So in our example, NaOH solution in the burette is a titrant. The volume from the burette is called a titr. So the volume of NaOH at the end of the titration is a titr. In our example here, we use HCl solution in the pipette. So HCl is our titrant. And the volume of the pipette is called the aliquot. In our example here, we need to determine the concentration of HCl. So HCl is our analyte. Setting up a titration, there are two ways that we can use. The first setting is when we have standard solution in the burette and we have the analyte in the pipette. From the pipette, we know the volume, that is the aliquot. At the end of the titration, we know the volume of the standard, that is the tide. Knowing 3 quantities out of 4, we can calculate the analyte. The second setting is when we have the analyte in the burette and we have standard in the pipette. So the pipette tells us the volume of the standard, that is the aliquot. At the end of the titration, we can find the volume of the analyte. Now again, we know 3 quantities, so we can calculate the analyte. From these two settings, we can see that analyte can be in the pipette or in the burette. More commonly, the analyte is in the pipette. There are 2 points of interest in titration. We've heard of equivalence point and endpoint. It is very important that we know the difference between these two. Equivalence point is a theoretical point at which the standard completely reacted with the analyte. So for example, if we have 25 milliliter of 0.1 mole per liter HCl, we would require 25 milliliter of 0.1 mole per liter NaOH to complete the reaction. So this means that the equivalence points happen at the volume of NaOH equal to 25 milliliter. In this case, we know the concentration of both HCl and NaOH. We know the volume of both, so we can predict or calculate the volume of NaOH at the equivalence point. But in practice, we don't know the concentration of HCl. So we don't know how much NaOH we would need. So we have to rely on the change of indicator. In our case, the color of the phenolphthalein changed from colorless to pink. The end point is an experimental point. It happens when there is a change in the solution. For example, the color of phenolphthalein changed from colorless to pink in the titration we're looking at. The difference between the endpoint and the equivalent point in terms of volume of NaOH or in terms of the tide give us titration error. So the end point is determined by the change of color of the indicator. So the indicator should have at least 2 distinct colors. In the case of phenolphthalein, we have from colorless in acidic solution change to pink in alkaline solution. the indicator must be added to the conical flask in a very small quantity. We will look at it. We will look at the reason for this later. What do we have to consider in an acid and base titration? For our current example, to determine the concentration of HCl from the standard solution of 0.1 mole per liter NaOH, we need to know the reaction between HCl and NaOH. This means that we need to know the stoichiometric factor or the mole ratio of the acid to the base. We need to know the volume of the pipette accurately. We also need to know the volume of NaOH delivered from the burette accurately. In order to have accurate volumes, we need to know how to calibrate glassware. We have to use the concentration of the standard to determine the concentration of the analyte. So we need to know what we can use as a standard solution and how to prepare the standard solution. We see that we relied on the indicator to determine the end point of a titration. So it is also very important to choose the correct indicator. Regarding the mole ratio of acid to base, I'd like to stress that the concentration of acid is not always equal to the concentration of H+. For example, in a monoprotic acid, 1 mole of acid contains 1 mole of H+. Say, for example, 1 mole of hydrochloric acid gives us 1 mole of H+. Diprotic acid contains 2 H+ in 1 mole of acid. For example, 1 mole of sulfuric acid gives us 2 mole of H+. Similarly, a triprotic acid contains 3 H+ in its molecules. Look at the example of phosphoric acid. The formula is H3PO4. So we can see that 1 molecule of H3PO4 gives us 3 H+. Similarly, looking at the formula of barium hydroxide, we can see that every 1 mole of barium hydroxide gives 2 mole of OH-. This means the concentration of barium hydroxide equal to half concentration of OH-. This is a very important concept that you must remember for acid and base titration. The concentration of acid is not always equal to the concentration of H+, and the concentration of base is not always equal to OH-. Now, we have looked at acid and base titration. We have to draw out the similarity from acid and base titration for other type of titration. So overall, for a volumetric analysis, we need to know the reaction between the standard and the analyte. This reaction must be complete, fast, and its stoichiometry must be known, meaning that we must know the mole ratio for the reaction to do our calculation later. we need to use A-grade glassware. For very accurate work, we need to know how to calibrate the glassware, and we have to use calibrated glassware. This including the burette, pipette, and volumetric flask. We need to know what compounds can be used as a standard and how to prepare the standard solutions. And also we need to know how to choose the correct indicator for the titration. We will look at every of these factors in the later lectures. Now I have the setup of two titration. These two are acid and base titration. Would you look at them carefully and think which of the setting is better? The answer, the first setting is not ideal because of the use of the Teflon here, and we cannot see whether any air bubble trapped in this area.